Along this series of videos, we will have a look at how to create guided simulations in Bullet from scratch. Using the harmonic oscillator formula implemented in VEX, this technique will allow you to use animations to drive your dynamics, and hopefully will give you a better insight on how guided simulations work under the hood. We are going to talk a lot about vector, matrix, and quaternion operations, so I am making the assumption that you already are familiar with those topics. Please do keep in mind that this is by no means the only and best approach to do it, but anyway, I hope you will find some useful information on these videos. The harmonic oscillator formula is used to model oscillator systems like a spring, for example, that make it very useful for what we want to achieve, as you can imagine having your target on one end of the system and your particle in the other end. If you go to Wikipedia and look up for harmonic oscillator, and then you scroll down until you find the Damped Harmonic Oscillator, this is the formula that we will be using on the next videos. I'm not gonna go into a lot of detail of every single part of it, but I will explain you what you need to know to follow along. This formula is used to describe things like springs and pendulums, and we will be using it to force our particle to reach the target. If your particle and your target are in the same position as here, then it means that everything is in balance and there won't be any force applied to the system. But if their position is different, like here, then there will be a force that is proportional to the displacement, or the change in position between the target and P. In this case, we will be also using dampening. That's the second part of the equation, where C is multiplying the velocity. K and C are two positive constants. K describes how quickly P is gonna reach the target, and C is the damping, so it's gonna act as a resistance for P to reach the target. X is the displacement, and if we assume that the equilibrium happens when target P and P are in the same position, then every time that there is a change or P is not in the same position as target P, then there will be a force. dx over dt is equal to the velocity. So with this said, let's go to Houdini and start applying this formula. Inside Houdini, I already created one geometry node, and if you dive inside, I have one pig geometry. That pig geometry is plugged into an RBD configure. This RBD configure is quite useful because it's setting the name. In this case, you can see that I set the name to pig underscore, and it's also setting the active to be 1. But not only that, it's also, if you middle click, you can see that the geometry it's already packed. It's setting the attributes to the proper type. So active, it's an integer and it's a point attribute, and name is a string and it's a point attribute. So this gives you everything you need to start. Now we need to move the pig, because at this point it's just a static geometry. So for that, let's create a transform. I don't want to animate this by hand, so we are gonna make use of chops for that. Right click on translate, go to motion effects, and then select noise. It will immediately create a motion effects chop network. And inside, if you dive in there, you will see that it created this couple of nodes. The important one is called noise. This is the one that it's currently driving the position of your geometry. You can also see that it created this sort of pop-up. So what I'm gonna do is I'm gonna play with these parameters, and then I'll show you what parameters I'm using so you can set them to the same. So I end up with these values. Let's close this and see how it's looking. If you play the animation, you will see that it's moving in a noisy pattern. And this is gonna give us the proper input for our setup. We are gonna create two nulls. The first one is gonna be our initial geo, and the second one it's gonna be the target geo. The target we needed to move constantly because this is gonna be the target geometry, but the initial needs to be frozen. So for that purpose, we are gonna use a time shift. Let's set the frame to F start, so it's frozen on the first frame. And we are almost done. So let's create a loop network. Connect the initial geometry on the first input, the target geometry on the second input. This is our starting point for both the rotation follow and the translation follow. First, we will solve the translation setup and then we will do the rotation. So for now, let's not worry about rotations. There's one last thing I want to tell you before we proceed to the loop network, and is that this transform needs to happen after the RBD configure. I'll explain this properly later, but make sure that that's the case. If you put the transform before, the system won't work. So let's dive inside the DOP network, and the first thing we need to create is an RBD packed object. Let's change the name to RBD. The next node, it's gonna be a rigid body solver, And in theory, you could plug this to the first input. But I like to use a multiple solver because I never know if I'm gonna change my mind and I'm gonna add different solvers to the same system. At this point, we should have everything we need to have a proper simulation. Let's change some parameters in the RBD packed object. The geometry source should be set to first context geometry. And I want to override attributes, just in case I want to animate the active state in subs. If you press play, nothing will happen, but the geometry is already a dynamic object. Actually, if you put a gravity force, you can see the pig is falling. Let's delete the gravity and create a subsolver. Inside this subsolver, we will make the system for the target. Let's write a proper name. Let's call it target. Follow. Dive inside the subsolver, and we will do everything connected to the dub geometry. We need to bring the target, so for that we will use an object merge. Let's look for the target and make sure that you export this as relative path. Now you have the target and your current geometry, so we need to create a wrangle that's gonna allow us to create the targeting system. The last thing we will do in this video is write the formula down so we can remember it. And that's something I always do. I tend to write the formulas as a comment, so I don't have to go online and look for them every time I forget them. So I know it's force equal minus kx minus cv. And this is all the information we need to start writing our wrangle, and we will do that in the next video, so see you in that one. One thing we know is that the pig coming in the first geometry, here in input 0, needs to find the target. And for that, we need to have a way to compare them. So this geometry knows what is the actual target that it needs to look. And if you remember, the RBD configure creates a name. So all we need to do is that the geometry that it's coming as the initial geometry can look for the target geometry and then find if there's any geometry here that has the same name as myself. And if that's the case, then I'm gonna store that geometry in a variable. That's easier to show you than to explain, so let's do it. We will use a function called findAttribVal. And findAttribVal requires a few arguments. So the first one, it's the geometry that we want to look into. We know that we want to look into the target that it's coming on the second input, so make sure that this is set to 1. We know that the name, it's a point attribute, so let's set the type of attribute. We also know that the attribute that we want to look for, it's the name attribute, so let's write the name. And the last argument, it's the attribute that I want to compare. So I want to use my own name, and what this will do is the geometry that it's coming in the input 0. So that's myself, that's the geometry that it's coming from dubs. It's going to look at whatever it's coming in the second input, so that's coming from this object merge. It's going to check or look for the name attribute on this input, and it's gonna compare it with my same name. And if the name is the same, it's gonna store that inside a variable. So we are going to call that variable fgeo. F for found and geo for geometry, and we need to close this thing with a semicolon. So now we have the points with the same name, and let's put some proper naming here. This is gonna be target geo. Now let's start creating the actual equation. So first we are gonna create the variables. So the first one is k. That's gonna be a float called k, and we are going to assign a value that the user can control, that I'm gonna also call k. And the next constant is c, that it's gonna also be called c. Now click this little button here, and that's gonna create the parameters that the user can control. For k, we will use 1 as default, and for c, we will use 0.5. There's no reason behind these values, it's just something I want to have there for now. So let's create the first vector, and in that one it's gonna be x. And if you remember, x, it's the direction of the force. And for that, I'm gonna do a subtraction. That's gonna be p minus my target p. So we know that my current position, it's v at p, and the target, it's gonna be saved in target p. But this is gonna error out because of course we haven't created the target. So let's create the target first. The target is gonna be a vector, and I'm gonna call it target p because I already used that name down here. And target P, it's gonna be equal to the position of the point that we found using the find attribute val. And to get that position, we need to use an expression or a function called point. And I need to look for a point in the second input. I need to read its position, and I want to read the position from point FG. So this was the point that we stored here. So now we have the first vector, x. Now we need v, but v is the velocity of the particle in the actual simulation, so I don't need to create that. So we have everything we need. Now we can do v at v. So we are gonna add to our current velocity the result of this formula. So we know that the first element is gonna be minus k, and we want to multiply k times x. And I don't need to do this, but I usually put things inside parentheses because it helps me reading the formulas easier. And the next expression is c and v, so I need to put a minus c times my velocity. So if I go up a few levels, I activate my DOP network and I'm gonna display flag my target. Hopefully if I press play, this should work now. So you can see the particle or the geometry is trying to follow the target, but something is happening. I think this is a problem with the viewport, so I'm just gonna close the viewport and open a new one. Let's make the background black, and there you go. So you have a point that it's following a target. I'm gonna make sure that this is the viewport that we are always seeing. Let's dive inside the DOP network, and then inside the target follow, let's change this value to 10. You will see that the particle, it's gonna try to follow it much faster. And you can play with these parameters. If you start decreasing the value of C or the dampening, you will see that it's gonna try to reach it even faster, but then you have some overshooting. So depending on the effect that you want to achieve, this might be very useful. So make sure you play on your own with these parameters. I'm gonna keep this as 0.38, so I don't have so much dampening and the overshooting is not that high. Let's put some proper naming on this point wrangle to make sure that we know, or any user that picks your setup will know, that this is the target position. Now the next thing we need to do is the rotation, but we will explain that on the other videos. So see you in the next one.